Hi and welcome everybody to the lecture titled In-Band Wireless Full Duplex Communication Systems. We talked earlier about the key 5G technologies that are going to improve the performance significantly in terms of data rate, reliability, latency, complexity, and some other factors as well. But one of the key performance metrics that we focus a lot on it, and we still need a lot to improve in that direction, is spectral efficiency. So, example of the techniques that can improve spectral efficiency is the modulation scheme, the waveform design, the massive MIMO design, and some other techniques. But today we will talk about new technique called in-band full duplex. So what's this called in-band full duplex, and how does it improve the spectral efficiency, and what's the transmitter and receiver structure design of this technology called in-band full duplex? So before we explain in-band full duplex, let's quickly review the existing duplex systems in wireless systems. So we have what we call simplex, and we have half duplex, and then we have full duplex, and the new one that we are going to explain extensively in this lecture is called in-band full duplex communication system. In-band full duplex. So what's simplex? Simplex is for the transmission systems that send the data just in one direction. Example, TV signal from the satellite to your home, to your dish at home. FM station transmitting continuously information in the downlink direction to your antenna, to your radio, whatever. So these we call them simplex. The duplexing case, you can classify it under the category simplex communication. Half duplex communication is for the case when you can transmit and receive, but at different times, or basically you need to wait before you talk. You listen before you talk. Example, the devices with the police, with the cabs. Basically they talk, then the other listens, then they press a button so that they can take control and start talking, and the other party receives and listens. So we call this half duplex because you cannot transmit and receive simultaneously. We have full duplex, in which you can transmit and receive simultaneously, but using different frequency bands or different time slots. Example of this is the mobile phone, the computer network, whatever, the Wi-Fi. All these are using full duplex full duplex communication, where you can transmit and receive in parallel, but you divide these downlink and uplink in time or in frequency. For example, when the computer talks to the access point, or when the access point talks to the computer, which we call the downlink. Wireless devices in general either talk or listen in one band, not in both. Transmission and reception are orthogonal in time and frequency. This is what we call full duplex, by dividing the bands, the resources, part of them for the downlink, part of them for the uplink. But to use the same available resources in both downlink and uplink, this is something new. This is something that's radically different from the previous schemes. So this definition, where you can that states the fact you can transmit and receive simultaneously using the same resources, is what we call in-band full duplex. So we have full duplex already using our mobile phones, computers, with the network, but that we call it out-of-band full duplex. Out-of-band full duplex, because you are using different frequencies or different time slots for transmission and reception. This, you are using the same resources, time and frequency, for uplink and downlink, for transmission and reception simultaneously. So this will result in improving your spectral efficiency significantly, because now instead of using two links, you are using one link, one resource for sending your data and capturing your data, which basically doubles the spectral efficiency, improves the spectral efficiency per device. So imagine you have 1,000 devices. You are, instead of serving only 1,000 devices with the spectrum you have, you can now serve 2,000. So imagine how much money you save, or how many users you can meet their requirements simultaneously in the network. So this is in-band full duplex. This is one of the most important aspects of improving the spectral efficiency in the future network. But I need from you to really distinguish and make it very clear in your mind the difference between in-band full duplex and the normal conventional full duplex system that use out-of-bands, separated out-of-bands to maintain the orthogonality of the transmission. Now, as is the case with any new technology, when you bring some new advantages, it brings so many advantages, this new technology. In terms, it can double the spectral efficiency, it solves the hidden terminal problem, reduces loss of throughput, reduces large end-to-end delay, improves network secrecy. Amazing advantages, as you can see. But as is the case with any technology, when you introduce something new that can bring you some advantages and merit, you also have some other disadvantages or drawbacks and hindrances that prevent you from implementing this in a very successful manner. Now, the goal of researchers and engineers now to be able to harness this technology to mitigate its drawbacks and disadvantages in such a way we make use of the advantages and reduce the demerits as much as we can. So how can we do that? First, let's after we talked about the advantages, let's talk about the disadvantages. The two main disadvantages, which are the challenges: how to design a working full duplex transceiver that in which you can transmit and receive without causing interference to yourself, and how to utilize the full duplex capability to benefit the future wireless technologies, including 5G. So self-interference cancellation is the main research theme in this domain. You basically, this is about the fact that when you transmit your signal from your device, the signal comes back again to your receiver antenna, and this causes interference. You need to cancel this interference. You need to prevent it, because this interferes with the coming signal to your device. Yes. So suppose this is the transmitter, the full duplex node, and this is the user equipment communicating simultaneously with your node, and you are also you are receiving, and at the same time you are transmitting. So the transmitted signal, since it comes back to your to the same device, gets mixed with the desired signal that you receive from the user equipment. So the total signal you receive at this side is y equal the desired signal xs multiplied by the channel between user and node plus hi multiplied by xi plus z. So this is the received signal. Your goal, the problem in this design is this: your goal is to cancel this intelligently, to remove the effect of this, if you can, intelligently, using a certain design. So all the research in the literature is about this, trying to invent and introduce new schemes and methods and algorithms that can remove this interference term. We call this interference self-interference, eco-interference. So before we go and talk about the solutions for this problem, let's together think how we can solve this problem. Can you think of solutions to this problem? I can say, yes, there are some solutions. Let's, for example, say that you have, this is the transmitter, and suppose that this transmitter can have two antennas, one antenna here and the other antenna here, maybe array of antenna. And this, you form a beams that don't interfere with each other, and you use this beam for reception and this beam for transmission. So in this case, but make sure that the user is along the direction of reception. So using the same time and the frequency resource, you are able to receive your signal and transmit it. But this, you transmit it to where? To where? The beam here, the direction of the beam is not towards user equipment, yes? I'm talking about line of sight environment. In this case, to make this work so that you can transmit and receive simultaneously, you need to put some reflecting service, intelligent reflecting service that can reflect the signal back to the receiver so that you can really take data from it and allow him to take data. Now you can consider the transmitter in full duplex, the receiver in full duplex, or both of them, the transmitter and receiver. Another example that can help you mitigate this interference issue is what if you can utilize the millimeter wave capabilities? Yes, you have your transmitter here and you have your receiver. We said in millimeter wave, the polarization is not rich. For example, if you send a signal with vertical polarization, you receive it with vertical polarization. If you send it with horizontal, you receive it with horizontal. So what if the transmitter agrees with the receiver that I will use the vertical polarization for a transmission and the horizontal for reception. So this is R, this is T. And here at the receiver uses this for reception and this for transmission. Now, since the environment is not rich scattering, is not multipath, does not cause any changes to the polarization of the electromagnetic field, whatever polarization you transmit at the receiver, at the transmitter, it remains the same at the receiver. So to make sure you receive the signal in the vertical polarization, you receive at the receiver in the vertical polarization field. And the same with the uplink. This is for, let's say this is for downlink and this is for uplink. So in this case, you avoid the the self-interference problem at both the transmitter and receiver side. Both of them, they will be happily transmitting and receiving simultaneously, and therefore improving the spectral efficiency significantly compared to the other previous schemes, which is something amazing. I mean, something beautiful, that just by thinking about the features of millimeter wave, we were able to come up with a technique, a method that can solve this problem nicely. But the problem becomes really serious when you are in a rich scattering multipath environment, when you are working around 2 or 4 or 6 gigahertz, where you cannot make sure that the polarization is the same at the transmitter and receiver. Your signal gets reflected off so many objects and so many obstacles and items and stuff between your transmitter and receiver, and you don't have this feature anymore. So you cannot implement this method for the case of rich scattering environment. Now, this simple method that I just explained to you, it's patent worth thousands of dollars, even if not millions, that was patented recently by a company working on millimeter wave. How to make millimeter wave transceiver and receiver works in in-band full duplex communication. So just simple ideas like that can get you really a fortune. I mean, you can really make an impact with them. But just like, how do we come with this idea? You just understand the problem, you understand the characteristics of some systems, and you match them. You try to fit this into each other. Now let's, I gave you just two examples, two nice awesome examples of how to solve this self-interference problem, but these two examples are limited to certain cases where you have millimeter wave or you have reflectors and now beams simultaneously directing to the first idea, which requires not millimeter wave, it requires beams, direct beams, where, for example, this is the beam and this is the second beam, and this is the transmitter, and for the receiver to communicate in in-band full duplex, the receiver needs to, the reception beam should be in this direction, and the transmission beam here should be in another direction. Let's say here, this is the direction, another direction, so that this does not interfere with this does not interfere with this, and as you can see here, you transmit, and here you receive in a acceptable manner because they are aligned, they are seeing each other. But what about these two beams? For this to make sure that they can work, here you transmit, this we call it downlink. You transmit, you receive. Here uplink, the receiver has also not only to receive, he has to transmit simultaneously. But he's transmitting to another direction that cannot see this beam. So to solve this problem, you put here reflecting service, intelligent reflecting service, that once the beam hits here, it just directs it to the direction of the receiver beam at the transmitter. Okay, this is how you can solve. Then we have two nice, amazing solution for this problem, but with certain condition. For this solution, you need line of sight environment without too much multipath, and for the previous solution we need millimeter wave communication where you don't have any change in the polarization. But what if you have multipath and you have omnidirection? What will you do? Here is the problem becomes really significant, and now we will overview some of the techniques to solve this. So we have large power difference between the transmit and receive signal. Keep in mind that once you transmit your signal, the signal power is usually very high, yes, extremely high, and compared to the signal of the receive, the signal power here is very high, and compared to the power of the signal you receive from the user equipment, it's really huge, because the user equipment, when he transmits the signal, by the time it reaches the receiver, it becomes really tiny compared to the signal that you transmit here just right now. Why? Because this signal like propagates through large distance before it reaches the receiver. But while the signal at the transmitter, it just gets transmitted. It's not, but it didn't propagate through large distance. So there is no significant path loss in the signal that just got transmitted from the transmitter. But here, by the time it reaches the receiver, it's really low. So how to extract this low signal from very big interference coming from your own device? So you can do that by analog cancellation, digital cancellation, but this can invoke and cause high quantization noise in the signal of interest. So self-interference cancellation, let's talk about one case where you have the signal of interest I told you why you receive it with very low power, and even if you receive it with high power, the power of the self-interference gonna be larger. So you have this, the sum of two signals, one large, one really high, and one very small, very tiny, and one is extremely large, has large power. When you quantize them, you still have, like for the small signal, you just get two levels, but for the large signal, you get too many levels. So this is due to the reduction in the number of quantization level for the small short signal, you will not be able to recover it correctly without much noise. Why? Because you reduce the quantization, the resolution of your signal is very low now. How are you gonna detect the details of the signal? It's going to be tough and hard. So to deal with this, so digital processing needs analog to digital converter, finite bits of quantization. So here the signal of interest, which is in blue color, digitized with very few bits. And for 14 bits ADC, self-interference is greater than 50 dB plus the signal, only 6 bits after the quantization. So the typical self-interference is ranging between 50 to 130 dB, which is much, much, much greater than the signal that we want to receive correctly. So the point here to use higher precision ADC, but they are very expensive and very slow and increase your complexity and increase the delay. Unsuppressed self-interference results in reduced capacity for the full duplex system, which falls below that of the half duplex system. So we have self-interference suppression. Cancellation plays the most critical role in implementing the full duplex system. The technique that you use in self interference cancellation is very critical, and we need to be very careful with that. So in a system here, in a practical Wi-Fi radio, you have your transmitted signal. The main signal can range from minus 90 dB to 20 dB, which amounts for almost 110 dB main signal. And the harmonics, which we call them the side loops, are usually up to 80 dB. And then you have the noise and the signal, the other transmitter, which is around 50 dB. So here, imagine you are transmitting a signal with this power, and you're at the receiver side. You have you need to cancel your signal. You need to cancel this interference signal in such a way that you can still recover it with acceptable resolution and acceptable quality. So you have here in the receiver, you have 60 dB of analog cancellation, 10 dB for peak to average power ratio saturation, and 50 dB of digital cancellation. It's really significant and too much. So for this, for example, this is an example where you can example of a technique that cancel the self-interference on the analog circuit, where you have here your transmitter. This is the transmit chain and this is the receive chain, and you have here a canceller circuit in the analog domain before the antenna. So you take you take part of the transmit signal from here, and you cancel it from the signals you received from the antenna. But as you can see here, you increase the complexity a little bit because it's implemented in the analog and causes changes to the transceiver structure. So this is one algorithm that can reduce the self-interference implemented in the analog domain, and we call this technique passive. Passive because it's in the analog side. The elements are not active. So it reduces the electromagnetic coupling between the transmit and receive path. Antenna separation. Antenna separation is also another interesting technique that can be used to suppress the interference. It can suppress the interference up to 70 dB isolation. For another technique is the antenna cancellation, where you can use the antenna to cancel the interference. How do you do that? You at the transmitter, instead of using one antenna, you use two antennas, transmit antenna and transmit 2. You transmit your signal from both of these antennas in an omnidirectional manner, and your receiver antenna, you make sure that it has a distance of d from the transmit antenna 1, and it has a distance of d plus lambda over 2. Now, what happens from electromagnetic background? What happens when you make your signal, the front end difference is lambda over 2? Your signal, you will receive it in the opposite direction. So suppose the signal you receive at this receiver from this antenna is something like this. The signal you receive from this transmitter at this position is going to be something like this. So they cancel each other, and you get 0 here from these two antennas. So what remains? It remains the signal you received from the user equipment here, which we call it the desired signal in this case. So this is how you can solve this problem. This is one example that enables you to solve the problem. Another example, directional passive suppression. I just mentioned briefly at the beginning, where you can use the extremely directional antennas to localize your signal and make sure the interference between the transmit side and receive side is minimal. You can do that by achieving minimal intersection between main radiation loops of transmitter and receiver antennas. Other useful passive self-interference canceller, you can use absorptive shielding, polarization decoupling, combination of above two, and directional suppression technique. These are other examples of passive self-interference cancelling technique. Now, passive cancellation technique are not sufficient to support the high integrity full duplex reception. That's why we sometimes prefer to use digital baseband suppressing technique. Not only passive suppressing techniques, but also active self-interference cancellation techniques, which can be classified into analog and digital. Analog because the elements you used are active, and digital because you are designing the self-interference cancellation technique in the baseband circuit. So you implement it inside the chip, not on the RF chain. So for example, active analog, this we have by combining at perfect opposite self-interference signal with transmitted signal, a three-step process here. You create the reference signal, delay and attenuation adjustment, creating a self-interference null by combining the self-interference and its opposite. And then by doing so, you are able to reduce the interference to a very acceptable limit. Theoretically, it can achieve perfect cancellation, but it's very limited in the practice. So here you have you can also use the circulator. Here I'm going to go over several examples of techniques that can help reduce the self-interference, but we are not going into the details of them. We have the active digital component here, where you design it based on linear algebra, and you calculate the amount of interference mathematically, and then you calculate this and design a signal that can cancel this interference intelligently. For example, you have the active MIMO as well, time domain cancellation, which can exploit the null space in the antennas and accordingly cancel the interference. You calculate the interference and add the signal that cancels the interference. This is the key idea behind these, if you don't want to be too much involved in the math. But the point is to find the interference term and put a condition on it so that you make it equal to 0, and then you find the signal that can make this 0 by some mathematical design that exploits linear algebra and singular value decomposition and some other techniques. Now, the most important part of this lecture is to let you know that this self-interference cancellation and in-band full duplex is not just theory, is not just something that we just came up with it theoretically and we say we can do that, and you have several techniques, you have advantages and disadvantages, but this is a system that has been implemented recently by some companies like Coma Networks. This company designed a perfect transceiver design, transmitter and receiver, that can perform in-band full duplex transmission while doubling the spectral efficiency with minimal drawbacks. And not only in millimeter wave or just beamforming antennas, but also in rich scattering multipath channel, where it's really very challenging. Not only Coma Networks company, but also Raptor company, MSC. They also designed an in-band full duplex practically to transmit and receive simultaneously. And also Huawei technology, also they designed, tested multi-user MIMO and full duplex radio. Full duplex radio achieved 90% throughput gain. But as you can see, the main key drawback of this technology is the fact that it always requires significant changes in the transceiver design. Yes, for example, if you want to allow your user equipment to use this technology, then you have to change all the smartphones in the world. You tell them, please rechange your design or throw your phone and buy another phone so that you can make use of this technology. So it's not very effective for access. Other people will not be willing to do that. So therefore, this technology is limited. Maybe it's gonna be limited just in that downlink where you can serve multiple users. In the uplink, transmit and receive from where the user equipment, if you want to user equipment to have the in-band full duplex characteristics, you need to redesign the smartphone. I mean, it's gonna be affecting all the smartphones in the world and to be able to transmit and receive simultaneously. But like for that reason, the applications are limited somehow to certain cases, and most importantly, for the people who are interested in building backhaul networks where you need to transmit and receive just between two entities, not you are not working with the access network with the user equipments. So up until now, we can summarize the things we have talked about. That basically, first of all, the present progress in self-interference cancellation, both at analog and digital stages, can bring the self-interference power below the noise level, but for low transmit power, short-range transceivers are the good choice for full duplex deployment. See, short range. Why short range? Because in short range, the multipath, the rich scattering effect reduces, and you tend to have line of sight environment. Full duplex combines well with many other technologies as well, but also I told you the challenge associated with that. Full duplex with massive MIMO paves the way for full duplex deployment with millimeter wave. That's true. At network level, full duplex suffers huge surge of interference. At network level, that's why I told you it's good for point-to-point communication, not for the uplink, not for the multi-user scenario, like you have a base station and you want to serve 100,000 users. It's not gonna be very effective. Too much interference because it's omnidirection. The receiver is working at low frequency and it's omnidirection. That's very limiting factor for it. So of course we can exploit this technique for improving the security, improving the performance of several other systems. So there are many directions to go with, but most importantly, we have to think beyond that and think of solutions that can really make such a technology even applicable for the case when you have multiple access networks, because it has so many great advantages that can be worthy of investigation and worthy of the efforts. So with this, we conclude our lecture and we stop here and meet you next time.